All right, this is part 6 of the Module 5 lecture. In this section, we're going to talk about the hypergeometric probability distribution. All right, hypergeometric experiment is different from a binomial experiment in two crucial facts. Number one, the probability of success is not constant from trial to trial. And number two, the trials are not independent. This happens because in a hypergeometric experiment, we're sampling without replacement from a finite population. Let's see how this works with an example. In this example, a company received a shipment of 20 buckets with raw material. And the supplier, the one that supplies the raw material to this company, informs them that somehow 5 buckets in that shipment contain material that does not meet the specification that the company requires. So we said that those 5 buckets have bad raw material. So now a technician in this company selects 3 of different buckets for testing. So the question is this a hypergeometric or a binomial experiment? To do that, we need then to analyze the description of the experiment. So let's look at if you remember when we talk about the binomial experiment, we have 5 characteristics. Let's see if those 5 characteristics of the binomial experiment are met. All right, number one, we can say that we have identical trials because these containers are identical, so we don't know which container has bad material or good material, and they're tested exactly in the same way. So they follow the same procedure to test them. So we can say that we have identical trials. We have only 2 outcomes. Either the material in the bucket is bad or it is good. Now, the probability of success in this case, the container or the bucket contains bad material, it changes from bucket to bucket. And why does it change? Well, because once you take the bucket and test it, then you know that that bucket has either good or bad material. And of course, you're not going to test it again. You're not going to put it back with 20 containers and allow a random selection with that container that you know it contains bad material. That'd be a waste of time. So once you know that bucket is good or bad, you put it away, then you select the second bucket, and then you test it. And so, for example, in here I'm saying, let's say the probability of the first bucket is bad. Well, that will be 5 out of 20. There are 5 bad buckets out of the 20 in the shipment. So let's say that the first one was bad. Now, what is the probability of the second one being bad? Well, now is not 5 out of 20. Now it's 4 out of 19 because the bad bucket you already know is bad. You moved it away and you have only 19 buckets left and only 4, a total of 19 buckets and 4 buckets that are bad left in those 19. So the probability is 4 over 19, which is different from 5 over 20. Or perhaps you may have gotten a good bucket in the first selection and then a bad bucket in the second selection. Well, again, you have 5 of 19. If the first one was good, then you will have 15 out of 20, and you have 5 out of 19. So the probability is changing every time you take a bucket and test it. So the probability of success changes. Now, because this once you take a bucket out, you're affecting the probability, and as you can see, the conditional probability is not equal to the probability of that event by itself. Then you know that the trials are not independent because the probability of success changes as you are removing buckets from this population. And the final condition is that random variable counts the number of successes just as in the binomial. But we can see that conditions 3 and 4 here are violated. So this is not a binomial experiment. This is a hypergeometric experiment because the probability of success changes from trial to trial, and because the trials are not independent, and that is because we're sampling from a finite population. We have only 20 elements, and once we select them, we don't put them back, we don't replace them. So that causes the change in probability and the fact that these events are non-independent. All right, so that's an example that shows you the distinction between the binomial and the hypergeometric experiment. All right, so now in this case, we are going to have to use a different equation to calculate a hypergeometric probability. And before I explain this equation, let's look at all these numbers and see what they mean, all these letters. So capital N is the total number of elements in the population. In the previous example, that was 20. There were 20 buckets in the shipment. And R, lowercase r, represents the number of successes in the population. So in the previous example, we knew that there were 5 buckets with bad material. And that was a success. We were looking for the buckets with bad material. So capital N minus R corresponds to the number of buckets that have good material. So in other words, those are the number of failures. Capital N minus R. Lowercase n represents the number of trials. In the previous example, the technician selected 3 buckets. And X is the number of buckets with bad material that we're looking from that sample. So in other words, X is the number of successes in N trials. And N minus X is the number of failures in N trials. So let's say that in the previous example, you're interested in finding 2 buckets with raw material and you selected 3. So you will have X will be 2 and N is 3 minus 2 defectives. There'll be only 1 bucket with good material in the sequence of a sample of 3 where 2 have bad material and 1 has good material. All right. Now with this numbers defined, then we can see that the probability or the formula to obtain hypergeometric probabilities is in the numerator we have the combination of the ways of selecting a given number of successes from R successes in the population. And then the second combination formula gives us the way of arrangements that we can have of successes from N minus R successes in the population. And then the bottom is telling us the total number of arrangements that we can get without distinguishing whether there are successes or failures. So if you notice here, we're using the definition of the classical probability that we learned in chapter 4. All right, let's look at an example to see how we can use this formula. Again, this is the same example as before. So we have the population has 20 buckets, so capital N is 20. We have 5 defectives in this population, so little r is 5. Now, in the first part of this problem, the technician selects 3 different buckets or containers, and she's looking for 2 of the containers having bad material. So in this case, lowercase n is 3 and x is 2. In part B, we're selecting now 5 containers and we're looking for all of them being bad. So in this case, lowercase n is 5 and r is 5. All right, let's look at these 2 cases. In the first case, as we said before, capital N is 20 buckets, lowercase r is 5, the 5 successes, so 5 buckets with bad material, and n minus r, that means that 20 minus 5, there are 15 buckets with good material in the population. So for problem A, we know that we are selecting 3 buckets, and we have 3 identical trials. We're looking for the probability of finding 2 buckets with bad material, and therefore there is only 1 bucket with good material in the sample of 3. So now that we know all this, the values of these letters in the formula, then we can go and then write the formula for the hypergeometric probability for the probability of finding 2 buckets with bad material in a sample of 3 buckets. So now we replace all the numbers here, here, and here. And as I say here, this is a number of ways of selecting 2 buckets from the 5 defective buckets in the population. This is the number of ways of selecting 1 bucket with good material from the 15 buckets with good material in the population. And this is the way of arranging 3 buckets selected at random from the 20 buckets in the population without distinguishing if they have good or bad material. So that's how we calculate the probability. So once we write the formula like this, then we proceed to expand the factorials of these combination formulas. We write all the factorials. And in here, I'm showing you a way of simplifying this calculation. So let's take, for example, this 5 factorial. Then from what we learned in chapter 4, you know that 5 factorial is 5 times 4, 5 times 3, times 2, times 1. And 3 factorial, of course, is 3 times 2 times 1. So that you can see that I can write 5 factorial by 5 times 4 times 3 factorial, because 3 factorial takes these 3 numbers. So that's what I did right here. So I wrote 5 times 4, 3 factorial. In the denominator, I have 2 factorial, which is 2 times 1, and 5 minus 2 is 3 factorial. These 3 factorial cancels with 3 factorial, and I'm left with the operation of 5 times 4 is 20 divided by 2. That's the 10 I get here. In this other calculation, I expand the factorial up to the largest factorial in the denominator. And you can see that 15 minus 1 is 14 factorial. And so this 14 factorial cancel with this 14 factorial. And 1 factorial is 1. So 1 divided into 15, well, is 15. I use the same approach for the term in the denominator. I expand the 20 factorial to the largest factorial in the denominator of this term, and that is 17 factorial. So I cancel those two, and I'm left with these calculations. So again, I hope that you find this useful when you do these calculations, or you can use a factorial key in your calculator if you have one. Otherwise, this is a good way to simplify the calculations. Anyway, carrying out this calculation, you find 0.3158. So the interpretation of this result is that the probability that the technician will find 2 buckets with bad raw material in a random sample of 3 buckets is 0.13158, or 13.16%, where I rounded the 5A to 6. All right, for part B, now we are selecting 5 buckets, and we want to calculate the probability that all 5 buckets contain bad material. So now R is 5, X is 5, and again, N minus R is 15. So we still have 15 buckets with good material, but we're not looking for selecting any buckets with good material in this case. That's why the 0 here. And now in the denominator, we are selecting a sample of 5 out of the 20 buckets. That's why it's 5 here instead of 3 as in the previous case. Again, you expand these combination formulas into their factorial expressions, following the suggestion I made before of simplifying the factorials. You can do that, and then you find that you have this division. If you carry out that calculation in your calculator, you will find that this is 0.0000645. Interpreting this result, then the probability that all 5 randomly selected buckets have bad raw material is 0.00088. And I just realized I have a mistake here. This should be 0.0000645 or 0.00645%. I will correct these numbers and repost the slides. Sorry, I didn't realize I made that mistake. I will correct this number so that when you do the calculations yourself, you will find the correct number. All right, so this is how to calculate probabilities with the hypergeometric probability formula. Now, as any random variable, the random variable has a mean and has a standard deviations. So here's the mean of the hypergeometric random variable. Here's the equation for that. And here's the standard deviation for the hypergeometric random variable. Again, I'm not going to ask you any questions about this. I'm just emphasizing the point that any random variable has its mean and it has its standard deviation. And finally, I wanted to point out that if the population size is very large or relatively large, then the binomial probabilities and the hypergeometric probabilities are approximately equal. So if you have a sample size of, say, 10,000, well, you do better, or you can do the calculations with the binomial form.